So we'll now look at the modified Bessel functions. The modified Bessel functions are given by the notation I of nu and k of nu of order nu. They satisfy the following differential equation, which is modified from the original differential equation that we call the Bessel's differential equation. Note that there's a minus sign here, and the form of the term here is x squared plus nu squared in the differential equation. We call it the modified Bessel's differential equation. And so the second order differential equation, its homogeneous solutions can be written in terms of the two linearly independent solutions, and they are represented by these two functions, I nu of x and k nu of x. The first of these is, if we describe it completely, would be called the modified Bessel function of first kind, and the second, k nu of x, would be called the modified Bessel function of second kind. And they provide linearly independent solutions, and so an arbitrary solution to the homogeneous problem can be represented in terms of a linear combination with constant c1 and c2. So we can think of the functions I and k as cousins of exponential functions e to the x and e to the minus x. So the first of these, I nu of x, is like a growing exponential, and k nu of x is like a decaying exponential. And in particular, if x is large, we can show that I and k behave in this way. So I nu of x is proportional to exponential with a modified amplitude, which is decaying amplitude relative to this exponential growth. And k nu is proportional to this decaying exponential times this modified factor. And so this behaves for large x like this exponential increase, and this behaves like a decaying exponential, which is further decayed slightly more by this factor here in front. If we now look at these Bessel functions for small argument, when x is small, x going to 0, we have these representations. Function I behaves like x to some power n, where n is the order of this Bessel function. And so this is going to be well behaved. When x vanishes, it will vanish. Or when I equal to 0, when n is equal to 0, then it will approach a finite value, it will become 1. And so I nu of x is a well-behaved function, whereas k nu of x, these are the two cases represented here, k0 behaves in this way. It has a logarithmic behavior, log of 1 over x, and so as x vanishes, k0 blows up. Kn, when n is not equal to 0, behaves in this way, x to the minus n power, and so when x vanishes, again k nu blows up. And so we can say that k nu is singular for small x. And again, knowing this behavior that I nu is well behaved and k nu is singular is very useful in solving problems where we can make use of these properties. When we need to come up with a linear superposition of these two functions to represent a general response, we can make use of these properties.